Okay. What's up? So we're back trying to make a module for central simple algebras in the open source computer algebra research systems Oscar, which is a project written in Julia. So let me try to just adjust some volume settings. Does that change the... Oh, it does. Okay, so there's been a little bit of a mix up in my head between how we go about doing this development and how we're currently doing it. So originally I was confused about essentially how to access a lot of the functionality of Oscar. So Oscar's built off of some component systems. Specifically, there's like the ANTIC number theory components that consist of Nemo, Flint, Hecka. There is GAP, a system called Polymake, which I've actually never heard of before, and I'm gonna look it up. And then there's another system called Singular. So Polymake is for polyhedral geometry. It's kind of interesting. Right. So Singular has most of the functionality that I was pretty sure that I needed, but I've decided, after contacting some people and then hearing their opinion about what should be done, to go through and kind of rewrite a lot of this code, which doesn't do too much at the moment, in terms of just the kind of base access that Oscar provides us. So whatever functionality Oscar has available, without calling into directly Singular.jl. So there are functionality, and there is functionality, and there are algorithms available in Singular that we don't really need to use, to be totally honest. So let's also change this music, something else. Yeah, fuck it. Let's listen to this. All right. So, what is it that we're doing in the current code base? Well, we have a struct, mutable struct, that will allow us to define a central simple algebra. It's going to be a non-commutative ring, which is presented as a quotient of a free associative algebra by some two-sided ideal. And there's going to be central simple algebra elements. So these are just elements in the quotient ring. The data type for these elements, it's going to consist of parent, the central simple algebra that contains that element, and then the actual element itself. So that's kind of the quote-unquote data. So it's like a lift of the class of the element inside the quotient, to the free associative algebra. We've got a function is 0, so just check if we have an element inside central symbol algebra. Is it actually defined as an element contained inside the parent ideal? So the way that this algorithm works is effectively, I want to say that it's effectively, I think, some Grosvenor basis technique, which should effectively perform like a type of division. So you want to see if this element is maybe divisible, or can be written as a linear combination by all of the elements generating the ideal. I think that's the idea. And I think that there must be some non-commutative algorithm for doing that, which I don't know off the top of my head. For central symbol algebras, there is going to be functionality for being a unit. So that's just if we can compute the reduced norm of an element, which I think that we can. And then there's going to be functionality also for is 0. So just checking is an element 0. We just try to lifting it and seeing if that's 0, or seeing if it's contained inside of so is 0 is here, checking if it's contained inside the ideal. Is unit, first it checks if it's a unit in the overring, then it checks if it's 0 in the overring. And if neither of those two things are true, then we actually have to use the reduced norm. So that one hasn't been implemented yet. Then we've got some basic operations. So double equality, plus, minus, multiplication, exponent raising to power of integers. We'll have division left and division right. And I was basing a lot of this code off of what's available in the PBW. Can't remember if I was in PBW quotient or if I was in PBW algebra. So here's some additional functionality that we can do. Stuff like number of generators. The ones that I really want are probably gens. So getting generators for the central symbol algebra. What is the difference between these two? Gens returns element type of Q, and then PBW alg quo elm Q dot base string comma x for x in gens Q dot s string. Okay. This kind of seems like a, I mean, the S string is a singular call. Yeah, I wonder about that. This one's kind of interesting too. Show names, show special, print. I don't know what this is, expressify is either. Deep copy internal, I don't know why they have this either. So base.decopy internal. You take an element inside some quotient of a PBW algebra. Dict is ID dict. And then you make parent A deep copy internal of A.data with the dict. Huh. So for us, one thing that I want to do is I want to make a so I want to make a function which does let's see. So far we just have a central simple algebra function which should construct a new central simple algebra, and we just need to input a free associative algebra, an ideal, and the degree of the algebra. We should make some assertions about that, but maybe that's to do. So this part I'm gonna just delete. We've got a function, symbol algebra. So this is going to stay, I think. And I had two different kinds, but I'm actually just going to call, I'll put them both in. So so there's no longer Nemo elements. They need to be central simple. Actually, do they need to be Nemo elements still? They should just be field elements. Huh. So, yeah, I wonder. Let's just try field element, see what happens. And then what are we going to do? We're going to construct free associative algebra on two variables. And I don't think we need a degree bound anymore. And then we also don't need to do the Grobner basis, I believe. We'll make a call just to an ideal, I think. So here's where helps to go into the source code. And we go to the non-commutative algebra, free associative algebras. So the call is just to an ideal. And we don't even need to specify the ring, supposedly. So maybe in the introduction it tells us more. Nope. In the ideal. So it's just ideal R vector. Okay, actually let's leave that R then just to be specific. And then we'll call a new central simple algebra with this type. I think that should be fine. We'll get rid of Nemo. Get rid of Nemo there. And also here. I wonder what the free associative algebra type operates on. So there should be some source code around somewhere. Okay, free associative algebra ideal. It's in the ideal. We don't have a base free associative algebra functionality. All right. I think it's fine. Okay, let's get rid of, we're gonna make the same changes here. So that, and then I think we should be good. So let's just do a quick little run through. See if it compiles, and also see if we can just make a symbol algebra. And yeah, actually I was just thinking, I don't know how this is going to, well, that's a different problem. That's this. Actually don't know how, so I haven't made any way for, I don't think I've made any constructors for the central symbol algebra LM type yet, which makes me kind of wonder how they do it in the PBW algebra case. So these are things that would probably just be nice to have. Kind of wonder what Expressify should really be doing. So we might be able to just search the code base for that. If not, then we try good old Gemini. And then in the meantime, start trying to do this. So QQ is rational field. So we'll say A is QQ minus 1. And then A is symbol algebra. A2. Oh, CSA dot. And what's the error that we get? So no method matching main.csa.central simple algebra. The type main.csa.central simple algebra exists, but no method is defined for this combination of argument types when trying to construct it. And so the issue was that we had method error. No method matching main.csa.central simple algebra, abstract algebra, generic, free associative algebra, Oscar. Is it the problem that, I mean, it says that the error is with Oscar.free associative algebra.ideal, whereas we have Oscar.free associative algebra ideal. That's the same thing. And then int64. this makes more sense, right? Of having an error of .generic.free associative algebra. But it is bringing up the error with the Oscar free associative algebra ideal T. Okay, we're gonna have to look that one up in a second. So, in the powerful computer, the expressify function plays a crucial role in transforming mathematical objects into structured expressions, paving the way for high-quality plain text expressions such as law text and HTML. This seemingly internal mechanism is fundamental to how Oscar achieves its rich and rich. As core takes an object from the Oscar and converts it into an intermediate structured format. Okay, so expressify is kind of a prettifier. Okay, and then we have to figure out, so got a free associative algebra, we got an ideal. Let's try just running these two things separately. So is this the error? Oh no, it's got to be. I mean, let's try just degrees. Yeah. Okay, so first of all, did not know that Control L clears the, or maybe just takes you to the bottom. So let's try 2A, 2A. And let's try the same input, but with R here. Type of I. Oscar.free associative algebra ideal of abstract algebra generic free associative algebra. And type of R. Maybe these T and these, maybe this T and this S is the real problem. The error message said specifically, no method matching this, and then it didn't like specifically this, which makes me think that maybe T is actually I almost want to put just straight up like this. And then and we clear and run it again. Using Oscar, using .csa. And now let's take QQ. A is going to be -1. And we're going to try to define a symbol algebra. AA2. And we get an error again. Doesn't like the innermost type still. Okay, here's something that is easy to do. So new chat. Can you help me debug a method error in this code? There's a type conflict with this struct. I'm kind of on the team that says that it would be easier to have an AI that's just integrated into your code base, which I could host locally, I'm sure. It would be nice to have kind of, I mean, I could try doing this debug. I've never used a debugger. I don't know how it works. And does it catch things like this? I mean, or is it as good as just kind of telling me that there's an error? I don't know what. So this is interesting. When you define a new type as a subtype of an abstract type like NC ring, you are making a promise that your new type will adhere to a specific interface. Need to have parent element types, constructors to make 0 and 1, basic arithmetic, equality, parent access. Sure. I didn't even print this part, right? Pretty much just did the same thing that I was already doing. So algebra structs methods. Thinks I should also have a base ring, huh? What? That is hard to believe. So if I just have, let's just call these two things. And then let's try to make some algebra with R, I, and 2. Maybe I have to make it with the CSA dot. It is possible that this is right. Let's see then, what is an NC ring? Sick. So it does feel like, where would the types even exist in this? Yeah, so M polytypes, I don't think so. Module scheme, the algebras, M polytypes, source types, yeah. Where is this though? NC ring. That's the only instance. Why did this pull up? Let's ask Gemini. Okay, well, we want to see the mutable struct for an NC ring. So far, we haven't seen it. All right, we can try. We can try to do this. I don't think there's shit in there though. So we need to do something for parent type, LM type, parent type. Things like this. So let's see. We need to figure out somehow what is contained in the data of a NC ring. So how do I use this test ring interface? Oh boy. Okay, so we need core structures, parent, type, base ring. We need constructors for 0, 1 second. All right, let's hit it up. And before we do that, let's read this interface. So the ring interface. ColorfulAlgebra.jl generic code makes use of a standardized set of functions which it expects to be implemented for all rings. Here we document this interface. All libraries which want to make use of the generic capabilities must supply all the required functionality for their rings. In addition to the required functions, there are also optional functions which can be provided for certain types of rings. If implemented, these allow the generic code to provide additional functionality for those rings, or in some cases to select more efficient algorithms. Most rings must supply two types, a type for the parent object, a type for elements. For example, the generic univariate polynomial ring provides two types, generic polynomial ring, generic.poly. The parent type must belong to ring, and the element type must belong to ring elem. Of course, the types may belong to these abstract types transitively. Okay, for parameterized rings, we advise the types of both the parent objects and element objects to be parameterized by the types of the elements of the base ring. We advise the types of both the parent objects and the element objects to be parameterized by the types of the elements of the base ring. Oh, yeah, the base ring, like the coefficient ring. Okay, that's doable. There can be variations on the theme. For example, in some areas of mathematics, there is notion of a coefficient domain, in which case it may make sense to parameterize all types by the type of elements of this coefficient domain, but note that this may have implications for the ad hoc operators one might like to explicitly implement. ring element type union. Because of its lack of multiple inheritance, Julia does not allow Julia base types to belong to ring LM. To allow us to work equally with abstract algebra and Julia types that represent elements of rings, we define a union type. So far, in addition to ring LM, the union type includes the Julia types. Okay, parent object caches. In many cases, it is desirable to have only one object in the system to represent each ring. This means that if the same ring is constructed twice, elements of the two rings will be compatible, so far as arithmetic is concerned. In order to facilitate this, global caches of rings are stored, usually implemented using dictionaries. Whether these global caches are provided or not depends on both mathematical and algorithmic considerations. For example, in the case of number field, it isn't desirable to identify all numbers fields with the same defining polynomial, as they may be considered with distinct embeddings into one another. And in the cases identifying whether two rings are the same may be prohibitively expensive. Generally, it may only make sense algorithmically divided. Okay. I really don't understand the caching yet, so we're going to move on. In the following, we list all the functions that are required to be provided for rings or by external libraries wanting to use this functionality. We give this interface for fictitious types. My parent for the type of ring parent object, and my elem for the type of elements of the ring. Generic functions may not rely on the existence of functions that are not documented. If they do, those functions will only be available for rings that implement that additional functionality, and should be documented as such. So data and parent object methods. So we need a parent type of my elem. Okay. So maybe Gemini is not lying to me. Let's see what this original stuff was. It says that I need things like parent type, which is the type like this. Okay, so that kind of does seem to check out. All right, parent and element types. So what should we call this? Implementation of the NC ring interface. Okay, functions required for NC ring interface. We'll have parent type, and it's going to be type of central simple algebra, and we're doing LM or what? LM, yep. So yeah. So I guess let's just do structs methods up here. Does it make sense to, I guess it doesn't really matter. I don't know. So I'm trying to make it organized. So structs. And then simple algebra is a constructor, but we're gonna have just right after that, functions required for the NC ring interface. So I don't understand this, by the way. Why would we write that? Oh, no, that makes sense. This is like declarative. So if you call parent type, then it's going to say, well, you're going to get the central simple algebra LM type T. No, I don't understand this. So we're going to do new chat. This specific method is designed to work with types from likely the abstract algebra package. At its core, this code specifies that for any given type T, the parent type of an element of a central simple algebra is the central simple algebra itself. Oh, okay. But where T? I don't like that. Okay, it puts parentheses around this and then says that is equal to T. Sorry, is equal to this. Okay. So we delete that. And we add where T. This actually looks okay. So yeah, the parent type of a generic poly is a generic poly ring. Yeah. We can look up or go back to the LM type is another one that we need, which I guess we just say LM type of such a simple algebra T, where T is going to be the essential. Yeah, okay. So LM type. So what is this thing doing? It's saying when you call LM type on the type of essential simple algebra parameterized by T for some T, it's going to return central simple algebra LM T. Okay, the other things that we need to implement are base ring type. On the type of a central simple algebra parameterized by T. And what should the base ring type be? It should be T, right? So is this information that actually needs to come along for the ride in this thing? I kind of think that, so let's see, R, so base ring R, rational field. And what happens if we dump R? So it contains attributes X and Y. Also has a base ring. All right, let's add it. It's gonna be first. Base ring. And I would say that this should be, this would have been what I thought was T, honestly. But we can just do field. This is fine. Doesn't have to be a field to be essential simple algebra, but we're using this. So now it's easier, I think. When we want to call the base ring type, what should we just implement? Field? Yeah, maybe we should just do this, right? I mean, I kind of don't think that we need a base ring. Data type. I mean, it could come along for free. It's in this parameter though, right? I mean, the T will parameterize field elements, so we can just call parent type on that. There's no real reason to put this in here. could delete this and assert that the parent of T is a field. It's kind of restrictive though. Let's just get rid of this. So what should this be? So the base ring, it should just be parent of T, right? Can I do that? What happens if I call parent type here? QQ field. No, we're putting it in then. But I don't want to lock it in on what it should be. Like field is really specific, but okay. Let's lock it in for field. And we're gonna go back. So it's gonna return r dot base ring. And we are going to enter F. F. Okie doke. Parent F my own. Parent. Central simple algebra LM T. Where T it's going to be F dot parent. This is the case with the parent object. So this is usually stored in a field parent in each ring element. For some element types, it isn't necessary to append the parent object as a field of every element. This is the case when the parent object can be reconstructed just given the type of the elements. Like a polynomial or something. Return true if every element of the given element type necessarily has a parent that is an integral domain. Otherwise, if this cannot be guaranteed, then the function returns false. So is this just because I'm in rings? Because now it doesn't make any sense, right? Like, is it a domain? No. And what does it say that I've got to include? Core, we needed this, which we've got. And constructors. So is 0. Check if we have this one already, right? So the constructors that I didn't put in were 0 and 1. Give me a minute. Where did I just start writing that crap? So let's see. I wonder if they have something that spells out how the non-commutative ring interface works. I mean, seems like they don't. Okay. So let's add in is domain type. Just naturally false is exact type. This must depend on the element, right? So you just think is exact type T? I don't know. So yeah, all right. Roll with it. So the stuff down here is going to be where I start making my own things, I think. So functionality. is going to be below. Everything up here is just going to be things that are required for the interface. So base.hash. Note that my LM may be parameterized. Blah, blah, blah. Okay, so it's supposed to return a hash for the object f of uint, of type uint. This is used as a hopefully cheap way to distinguish objects that differ arithmetically. If the object has components, for example, a coefficients polynomial or elements matrix, these should be hashed recursively, passing the same parameter h to all levels. Each component should then be XORed with h before combining the individual component hashes to give the final hash. Hash functions in AbstractAlgebra.jl usually start from some fixed 64-bit hexadecimal value that has been picked at random by the library author for that type. That is then truncated to fit an unsigned integer. This ensures that objects that are not that are the same arithmetically, or have the same components, but have different types or structures, are unlikely to hash to the same value. How the fuck does PDL and quotient do that? So in here you're saying there's a hash. And they just say revert to whatever it did before, huh? Function. Base.hash. A central simple algebra element. And h, an unsigned int. What are we going to return? The hash of a.data with h. End. And now, one thing that I'm wondering. Okie doke. So, I mean, I could split these up like this. All right. We're going back. So we've got to do a deep copy internal, huh? The hash functions will return a copy of a given element, recursively copying all components. Is this a new function I have to do? And it's going to be return central simple algebra element, parent of this guy, and deep copy internal of a data and dict. Okay, and then let's just check at the moment that that is fine. Yep. Okay, outer constructors for most abstract algebra types are provided by overloading the call syntax for parent objects. If R is a parent object for a given ring, we require the following constructors. Fuck. Oh, here are the constructors, huh? Alrighty. So there's going to be a function, which is just R, central symbol algebra. And it's going to return the 0 object. I should probably make a 0, huh? Okay, so we should just check in this case that the parent of A is R. And if it's not, then we say that it's some method error or some domain error. What kind of error should we throw here? What kind of error do they throw here? We'll just say element does not belong to algebra. And otherwise, what do? We just return A, right? I mean, A hat genus, really. That was an unexpected thing to see. This one I could see given some stupid error. If I say that the parent of A should be the base ring of R, they might be different rings in memory even though they're the same ring, right? Anyways, so otherwise we return the central symbol algebra LM with R, and the data should be R of A, R dot base ring of A. Maybe just R dot ring of A. Fuck. We haven't done 0 and 1 yet. So should I do is 0 with no underscore or with underscore? With no underscore, right? Here there's an underscore for some reason, I think. Yeah. Still have not done is 1, so and what are we going to return? Central simple algebra LM. That might work. Not entirely clear. It's not entirely clear. But we're going to try running it after all this is over. So. Canonicalization. So when fractions are created with two elements of the given type, it is nice to be able to represent them in some kind of canonical way. This is, of course, not always possible, but for example, fractions of integers can be canonicalized. In abstract algebra, the denominator would be made positive by dividing by both the numerator and denominator. For elements of a field, canonical unit simply returns the element itself. Finally, if A is U times B, we should have the identity canonical. For some rings, it is completely impractical to implement this function, in which case it may return 1 in the given ring. The function must, however, always exist and always return an element of the ring. Okay. So, function. Canonical unit. A. It's going to be a central simple algebra element. And what's it going to return? For now, it's just going to return A dot parent 1. And hashtag to do. Figure this out. Implementation not yet made. Okay, now we got to do string IO. So this should print an English description of the parent ring. If the ring is parameterized, it can call the corresponding show function for any rings it depends on. Fuck, dude, we haven't even gotten through like a small portion of this shit yet, right? Like, oh yeah, so we haven't even done that yet. It should be, so we should check. So if, so B is greater than 0, and if it's not, we could do greater than or equal to. So how do we do that? Equals greater. greater or equal. Or domain error. At the moment, we don't have any way of making this work. So implementation not made. Either, yeah, implementation not made for negative exponents. What else does it say that I need to do? I've gotten that. Optional but recommended if exact, deep copy, show IO. This actually, I probably should change. Just because the show IO, I feel like, is the biggest pain in the ass. Okay. So we're going to quit, which I think in Julia is exit. And we're going to run this again. See if all of it makes sense enough now to actually build essential simple algebra. So we're going to be using Oscar, using our new essential simple algebra package. F is going to be QQ, A is going to be QQ minus 1. And we're going to define a symbol algebra. And we got big ol' method error. You may have intended to import base.parent. The function parent exists, but no method is defined for this combination of argument types. And where, oh where? Oh, parent of QQ field element. Yeah. Okay, so somewhere in here. Right. This is almost certainly where the error is, right? Or here it could have been the same, yeah. It specifically says on line 27. Yikes. Okay. I don't know how to get around that one then. Parent of essential symbol element type is supposed to just be f.parent. That one you'd think would make sense. Okay. So let's try to figure out. Well, we can go through the problems like this, right? So method call error on. Do not want to look at that. There are some things to fix here. This one I thought made sense, and it says it does not like it. Oh, actually, I don't think it does care about that. Oh, because we're trying to call parent on QQ field elements. Right, sure. Yes. Okay. And so that is what the error is. So we could say parent type. Yeah, we would have to know what the field element functionality is, right? So let's try dumping A. All right, all we can do then is parent type, huh? I'm not sure if this is the right way to go about it though, because it's probably going to say like field element or something, right? So we need to see if, how do we see if two parents, how do we see if two things are in the same? So check parent. Big ol' error here. So check parent. It is used here though a few times. There's just no function for it yet. Check parent QQ -1, 2. Parents do not match. True. So I feel like every time I wanted that check parent type, I should have just used check parent. So we should have it here. I mean, this is kind of a cop-out, but and we should also have it here, I guess. And here. Actually, this one is a.parent. Okay, then we can just use check parent here, I think. Yeah, so how do I get a base ring out of QQ, out of a QQ element? That actually seems like it should be totally okay, right? So, field elem is just a ring elem, really. How many methods are there with field LM? We're looking for one that says parent. Yeah, it's actually weird that this didn't work, right? Let's delete that. Start over. Just have to remember now that we're calling simple algebra with the capitalized. So A is going to be QQ minus 1. And then A is going to be CSA dot symbol algebra. Like that. And we got an error. QQLM has no parent. Yeah, where was that? Get property in 49. So somewhere we're calling parent on a type. The one place that it makes sense is kind of here that could happen. I could also see something along the lines of like making a, so let's try, so it probably doesn't have anything to do with being simple algebra, right? So let's just try running these commands separately. My favorite. Right, and now we do A is central simple algebra of AAA. That's not how this works. So we got to do QQ RI2. No matching method. Closest candidates are some stuff. Show error. And now we get Gemini to debug again. Yeah. There still seems to be an error in the following code. Do you know what it is? Is that still an issue? Yeah, okay. You think that this one actually is good, huh? So let's try this parent of that. Does that give me something? And one parent of this guy. Yep, all right. Exit, try it again. Okay, so we're going to define element QQ minus 1. And then we're going to make a symbol algebra. Like this. And we get no method matching this. So after making that change, I tried running the symbol algebra command. I got this error. I can actually do this though. Right, so this is where I thought it was, right? Your code defines a method for parent. However, because you didn't explicitly state you were extending the base.parent function, Julia assumed you wanted to create a completely new function called parent that is local. So when you call this the code, inside it calls this. Import the functions you want to extend. I don't know if I do want to extend any function. So just the parent of such an element should be... so how does this get around this? It did the same thing. F.parent. Alright, so let's see. The error message even hints at this. You may have intended to import base.parent. You're also extending several other base functions. You will run into the exact same error for each of them as soon as you try to use them. The correct fix is to import all the base functions you're extending. Is it? This can't be right. So it says look up exterior algebra. .jl. I'm doubtful about some of this. So, method error, no method matching parent of QQ field element. That seems to not be true. Right? Because calling parent of QQ1, for example, we'll say QQ. So, you think that this is going to work? Import base parent. And then if I call this, suddenly what? It's going to work? I am hard pressed to believe that this is going to do it. That actually changed a little bit. So what if I say using abstract algebra? Not sure if that's going to be a good idea. Let's run it back. So So you think that using Oscar would include abstract algebra? But it's like not seeming like it, and now that's definitely not right. Okay, definitely don't use that one. Yeah, Oscar should just import all of this stuff, right? I mean, like, so I'll ask, so how come, why doesn't Oscar import these functions? Why aren't these functions included in the using Oscar line? Oh, so if I import Oscar, no way. I just using this. Whoa. So that didn't do shit. Yeah, I am wondering, so I think, okay, so let's say, okay, so just to clarify, so let's say I want to incorporate my code into the Oscar environment in the future. How do I, is there a way to test as if it has access to all of the imports as in Oscar, e.g. Can I write something? Can I include a line? I should have downloaded Oscar locally. That's probably it, right? I have to download Oscar locally. Fuck. I think that is it. I think that when you make, yeah, I think that when you make, okay, so so the idea is, all right, it's a lot of fucking pull requests in my mind. Okay, so This is the yes, absolutely. That's a very practical question. You want to develop your code in an environment that perfectly mimics this internal namespace, so you don't have to guess which functions are available or manually import. There are a few ways to achieve this, ranging from a quick interactive trick to a more formal package development approach. Method 1, quick and direct. You can command Julia to run your code file from within the Oscar module itself. This means your code will be evaluated as if it were literally typed inside Oscar source files, giving it access to all of the internals. The way that you do this, load Oscar package and the indispensable revise package, which allows you to change your code without restarting Julia. Use the base include function to include it into the Oscar file. What happens? This is the best practice. This is probably what I should have been doing. So, well, the include trick is great for interactive testing. If you plan to maintain this code long-term and distribute it, the best practice is to set it up as a proper Julia package that depends on Oscar. This is the method you would use if your module were to become its own package. Generate a package. Julia has built-in tools for this. Add Oscar as a dependency. You'd find a project file. I've got this already. Oh, but it's not a dependency. Oh. Oh. Hell yeah. Let's do that. Open in terminal. CD this, CD this, that. And there's two things actually that I want to do. So one of them is remove packages and one of them is add package. So activate.csa. Kind of curious if that just fucking did a bunch of shit that I didn't want it to. Okay, how do I make sure that I'm not just making a bunch of crap in here? I mean, what is that even? Okay. So let's, how do I activate? So I have a package in Julia. How do I what does it mean to activate it? Created using the generate function. So there's a couple things that we're going to do. We're going to remove the singular enigma dependency, and then we're going to add an Oscar dependency. I want to know what it means to... if my package has been activated in the past, will running activate override this? I mean, how am I supposed to access the thing that I should have already probably have done before? Okay. Okie doke. So we are going to go here, activate. We are going to rm Nemo. To remove a dependency in this package, do I just call rm the dependency? Okay. Kind of vibing, right? Okay, so after doing this, we should be in the spot that I thought I was before I started, which was that everything can just run, and we'll have our own type system, and by that I mean we have our own type called central simple algebra. combined with its own elements. Ideally, what I want, in order to actually call that like its unique little type, is some way to check that it's a central simple algebra. But I don't know at the moment how I would actually do that. Okay. So we should be good there. It's never good when this doesn't auto close. I feel like this means that my computer is about to explode again. Let's try that. Run this time. Let's see what happens. Oh my gosh. So if I wonder if I even need to use Oscar like that anymore. So yeah, that's actually good enough to ask about. I'm making a Julia package. Do I need to include using blah for each dependency blah in my package? Manifest .toml file. It was really in the project file, so seemed to figure it out. Yeah, I meant to say in my project file. Let's see if this is going to be good still. So thank you. That was pretty much what I was asking. Alrighty. So now we do A is this. And it doesn't work. Okay. So same error. Huh. That's not fun. So I was hoping that by including Oscar in the dependencies, that would somehow also include like the base. Yeah, so I'm kind of curious. It looks like, yeah, so it looks like Oscar has a, so, yeah. All right. Okay. I have a question. So here's a question. In Oscar.jl, there is a file with a list of imports that are made. In my package, I seemingly do not have access to these imports while only listing Oscar as a dependency. Is there a way to incorporate these imports without having to copy them all separately? I didn't even get a full coherent sentence down, but I think it figured it out. Probably. Usually does. The difference between what a package uses internally and what it exports for you to use. Huh? Simply adding Oscar as a dependency and writing using Oscar in your package will not give you direct access to all the functions it imports from its own dependencies. Here's a breakdown of why this happens and what you can do about it. The why, namespaces, and the export key. Think of Julia modules. Think of a Julia module as a room. Using some package or import some package. This brings the some package toolbox into your room. All of its tools are inside, but they're still in their own box. Export some function. This is the package author taking some function out of their toolbox, placing it on the main workbench for anyone who enters the room to use easily. It's kind of a confusing way to talk about namespace, honestly. This is like, I still have to call something like Oscar.function in order to operate with a function. Although now I can see that that is a function I can call. Here it's like I can just call function. I don't have to use the specification of where the function is located, is what I think that means. Oscar.jl is a massive computer algebra system that is itself built upon many other powerful packages. Inside the Oscar room, its developers have written import Nemo some function and using Heka. This brings the Nemo and Heka toolboxes into Oscar's room for Oscar's own developers and internal code to use. However, the Oscar developers have deliberately chosen not to export most of those functions. They have carefully selected which functions to place on the main workbench. This is a very important design principle. Prevents namespace pollution. If Oscar re-exported every function from all of its dozen dependencies, using Oscar would dump thousands of functions into your environment, making it highly likely that names would clash and it would be impossible to know where a function came from. It provides a clean API. So how do I access these functions? You have two main paths forward. Path 1 is the highly recommended best practice. Add the dependencies to your own package. This is the standard, most robust, and correct way to handle this. if you need functions from Nemo or Heka, you should consider them direct dependencies of your own package. Find out which underlying package the function you want comes from. For example, matrix space comes from Nemo. Number field comes from Heka. Add it to your project. In the Julia REPL, activate your project's environment and add the needed package. Now you can use it in your code. So I need effectively like all of these imports. Not all of them, but re-exporting. Well, not generally. No, I'm not going to do that. 3. Use your local module. In your main package file, you would just using your local module. Nah, I don't want to do that one. Okay. So I want to import base. And specifically these functions that I'm calling. Okay, so I have functions that should extend the base functionality, e.g. parent plus minus equals equals how do I add these dependencies coherently? I think what I'm going to have to do is I'm going to have to open a terminal. I'm going to have to probably go to this thing, go into here, open a Julia REPL. Okay, so I am supposed to import just a fucking bajillion functions, huh? Which ones? So, I think actually a bunch of them. So we want plus, minus, star, caret, equals equals, deep copy internal, hash, 1, parent, zero. I think that's all of them. Now we run it. And we try using Oscar, using this module, define a element, try a symbol algebra, and we got an error. No matching method. The type exists, but no method for this combination of arguments, of argument types. This combination of argument types when trying to construct it, but no method is defined for this combination of argument types. So what is the error, more specifically? It's just this bullshit. I mean, it could be this, so let's try running this again. And then this one is not going to work. So we'll just type it out. And now we do A is central simple algebra with these inputs, and we get kind of the same thing, and all of this comes down to the type of I. Being an abstract algebra generic free associative algebra element. Oh. Elm, huh? Crash that shit. Let's start it over. Fuck. I put it in the wrong spot. Alright, I typed quit after that. It's supposed to be exit, so we'll just delete, start again. Man. I kind of get it. If I could, like, somehow just... Maybe there's a better way to edit code than doing this. I could see that being true. Really? So R XY is free associative algebra on these variables. Sorry. And I is an ideal in there. Let's say generated by X and Y. Type of I. So I mean, I'm just gonna add everything. And see if that just fixes it. So I kind of wanted it to be, well, I wanted it to be a little bit more free, like not having Oscar here. But maybe we can't. Ooh. Ooh. So now, okay, cool. So now there's literally nothing I can do now, right? Like, yeah. So that is good though. That's a start. So the next thing that we're gonna do is we're gonna work on trying to make it so that central simple algebra has elements, and those elements are given to us in the terminal, and we can add them and multiply them and things, and they'll return values that make sense. Okay, so what's down here is tensor product of two algebras, but we can't currently use algebras, so it's not so useful, to be totally honest. So here are the so the main structs of the new type. So structs of the central simple algebra. So I kind of want to say like new structs. Simple algebra and central simple algebra LMs. Functions required for all for using the NC ring interface. And then after all of that, so we're gonna have simple algebra functionality, I guess. Constructors functionality down here, which I have not done anything with yet. And let's see. So one thing that we want to do is figure out a way how to I mean, it would be cool to actually just instead of printing out all of this, just print out like central simple algebra over the rational field or something like that. Of degree blank. This is what I'm gonna say. Yeah. So that's probably the show function that I didn't want to fuck with. And the last thing to do after that, let me try to. So the last thing that we should do after this, if I turn this all the way. Okay. If it's all the way down, it's pretty okay. Yeah, okay. So the last thing to do is to think a little bit about how we represent elements, right? So I know that A is now an algebra. And if I do something like A.ring, if I do gens A.ring, right, this displays them. And so if I do xy is gens A.ring, x plus y, type of x plus y. Right. So what I want it to do actually is I want to output in the central simple algebra function effectively the generators. This is what makes it a little bit tricky, is that the generators are not very clear for like what is a central simple algebra, right? It's not always generated by two guys, probably. So we need a way to make the generators accessible. We need a way to say that when we have generators x and y, when we add them, they're actually adding as generators. The big thing there is, I think, when we do things like plus, minus, star, exclamation, or like this caret. I think actually what I'm going to put here is like normal form. So for example, if I did like x cubed plus y cubed, and I wrote out normal form of x cubed plus y cubed with a dot ideal, wonder what's going to happen. Minus x minus y. That was not very expected. But that's kind of what I wanted to display next. And ideally, I guess that would just be in the show, right? So I think actually we can make it so that all the algebra happens before it actually gets committed. I don't know if that's good though. So like, for example, right, let me just check what the type of this thing is. I think it's just going to output another element. Okay, so one thing that we can try doing is do something like this, right? Like that makes sense. And we could do this. And that makes no sense because I didn't add the a dot ideal still. Right, like that. So I want to make it so that when you interact with these guys, so there should be a function I think that calls effectively the generators for the ring here. And then you have to probably redefine the generators. yourself. And then once you start working with those, writing them to screen, they'll be considered elements of this Central Simple Algebra element class. So that is the current idea. And we're going to look inside of the PBW algebra quo to see if they implement something like this. So this base.show, I still think I need to incorporate function gens. It's going to be lm type of q, and then I think brackets, it's going to return some list. So for x in the generators of the singular ring, it's going to return back, right? So it's going to return back basically a list or a vector. I don't know what the lm type of q does there. lm type of q. That might just dictate what the types of... I can't tell what that thing in the front does. So here though, we'll just define, right, so it's just going to define PBW alg elements for q.I base ring x. Right, so that's just going to be doing effectively what I wanted. So gen, on the other hand, oh, this will take the ith one, I guess. I don't know if I care about making that function. Simplify is something that we could implement as a function where we just call the normal form on the element. Yeah, so I guess it depends on how we if we either do the algebra and then reduce, or if we do all of the algebra and reduce at the same time, I guess. So it's either, so I guess, what do you think is more performant, Jonah? Yeah, so what's best practice? When considering quotients of polynomial rings, does arithmetic of polynomial elements happen, and reduction all up front, reduction at the end, or are operations intermixed? Arithmetic reduction. So I'm kind of curious, just in the sense of like, how do we go about actually thinking about these elements? So I mean, kind of one of the useful things here is that this normal form actually allows us to effectively reduce, right? Okay, I kind of agree. But also, what is this normal form? The theoretical foundation of normal forms. So when you have a quotient ring, is an ideal, you are working with equivalence classes. To perform arithmetic, we need a unique canonical representative. This unique representative is called the normal form. The standard way to achieve this is by first computing a Grosvenor basis. The normal form of any polynomial then is its remainder after division by the Grosvenor basis. So the mathematical definition of multiplication in the quotient ring implies a two-step process. Multiply the representatives, find the representative. The question becomes, if you have a long computation, like f star g plus h times k, when do you compute the normal form? The practical answer, taming expression swell. The core issue is expression swell. I could believe this, that you could get some exponentially long number of multiplications. Okay. Okay, so we're gonna go back and edit. Okay, we're gonna go back and edit these. So let's put a to do here. Incorporate the normal form of arithmetic of central simple algebra LMs. And we also need to make it so that we can actually call in some reasonable way this this algebra. And then we're looking pretty good. I mean, we have to do a lot in order to actually get something that's like workable. We haven't even gotten to the algorithm part of this process, but we've gotten into what I would call a good spot. The thing that's going to be interesting is doing, so I'm going to do group cohomology. So this is just the central simple algebra package. I'm also planning on doing a group cohomology package. And for the group cohomology package, a lot of the functionality is not going to work, I guess is what I should say. Like or it doesn't have any like predefined functionality. So we're gonna have to do like set maps, and we want to do stuff with groups. So actually, maybe Gap has some functionality in it. Sorry, I meant to click groups there. So I'm kind of curious about. Actually, we got homomorphisms, we got groups, G sets. This file contains code related to G sets. The idea of the implementation is available with gap functionality for computing orbits, permutations, actions, etc. Actually, it's super interesting. I mean, how are we going to do this? But yeah, this is definitely going to be the harder one, right? Okay. Yeah, for now, we're going to keep on thinking about just the central simple algebras. So I want to take like a little breather and just go get up, move around for a second, and Grab some food. But let's see just one thing first. Okay, I'm gonna go do that. I'm gonna get up and get some water and grab some food.
Meet Asana, a work management
Nope.
platform that
No
helps
ads. Okay, I decided that I need to make a screen that says "We'll be right back." But in the meantime, I got an email that I need to respond to, and also okay. Also, I feel, I don't know, significantly better. So let's see. Now, the big thing is actually to figure out how to call some of these elements. So this I should be able to close, and I expected that, so here we go. All right. What do we try? So we try we need to get somehow way to construct elements also to pull out generators. And I want to edit the show for, so this is one that I'm going to do here, I think, first, which is okay, a couple of things. So let's go to the Oscar.jl package. Let's look at what their imports are. Show is one of them. And abstractalgebra.jl. In the rings interface, there's a special thing that they say about the show. So it should be show IO, my parent, and also from my element. Okay, so it's not clear to me what I should be calling here, actually. Or where I should call it. So we'll do just here. Function base.show. And it's going to be central simple algebra. T, where T. And this should print an English description of the parent ring. Okay, so PBW does what? It just @show name. So is there a list of macros somewhere in this source code? What about the show special, I guess? Hmm. All right, let's try. Let's try. First, just running this. I think the is terse thing will still happen, but feels like I shouldn't need to fuck around with that. All right, let's see if we can not troubleshoot these, but Hmm. Good. I'm a little bit out of it. Now we're just copy and pasting. I'm not sure why this function base.isTerse needs to be incorporated. And in fact, it looks like it cannot be. So, warning, could not import base.isTerse into CSA. Yeah, let's see if I can find something inside of Julia's, sorry, the abstractalgebra.jl's interface in some way. So first one went to just some crap. Wish I had a better way of searching through there. You think that's it? Doesn't entirely look like it. Actually, kind of does. Okay, so. See if that runs. In the meantime, we'll go here. And there is a terse here. Is terse. Comes from abstract algebra. So I feel like I shouldn't need to import it if we're using Huh. Is that really it? Come on, this can't this can't be right. I'm fucking running out of steam a little bit here. So no method matching get, type, main, this stuff, symbol, bool. So let's just check the abstract algebra pretty printing interface. See if we can get a direct from the source. So what would we call this? Show name? Show special? That's actually what I wanted. Pretty printing. So we provide macros to change the way certain objects are printed. In compact and terse printing mode, show name tries to determine a suitable name to print instead of the object. Show special checks if an attribute show is present. If so, it has to be a function taking IO, optionally a MIME type, and the object. This is then called instead of the usual show function. All are supposed to be used within the usual show function, where at show special elem is only relevant for element types of algebraic structures. At attributes, my object. If the object has a show attribute. This gets called with IO and obj and returns from the current scope. Otherwise does nothing. If obj does not have attribute storage available, this macro does nothing. It is supposed to be used at the start of show methods as shown in the documentation. Examples: polynomial ring, cache equals false. Univariate polynomial ring and X are the rationals. If the object has a show attribute, this gets called with IO, mime, and obj if applicable. And IO and obj otherwise returns from the current scope, otherwise does nothing. Okay, I'm just not calling these correctly. Is what I'm. Well, I knew that from the start, I guess, but how does this one do it? Okay. Okay, so I don't need anything to do with attributes. We just need the show name. So this is kind of not important, I think. I feel like let's just see what happens, I guess, when we run this. And we don't need to do that anymore. Okay, so how did the show get messed up here? So system REPL showing an error caused an error. Oh, I should have done something like, let's just try at show special. See if we can get away with no. Okay, now we try Oscar. Okay, using Oscar. Using this thing. Nothing was printed. I guess that's somewhat interesting. Maybe it just eats it. Hey. Okay, so I think this wasn't maybe reading this right, but it looks like it does just eat the output. So for example, usually if you call a polynomial ring, supposedly maybe you get univariate polynomial ring in X over the rationals. And if you say abstract algebra dot show dot at show special macro, then it should take standard out and R. Okay, so let me think about this. So if I set attribute, it's going to change some stuff. For R with show and input out, it's just going to go to print input and then always the one true ring. So now you do the same thing and it is printing the one true ring. And now when you do R, show for R uses this at show special. For R, I guess. So do I just do I just I think I just do something like this. And we'll say something like essential simple algebra over do R dot base ring and of degree R dot degree. Okay. Try this, and I think this will be the last thing that I do. Girlfriend wants to cook. I'm also totally cooked. Just burnt out. So we'll just go in order. Oh, look at that. Central simple algebra over rational field of degree 2. Oh, that's neat. Oh, that's very neat, right? So I feel like I can just do this. Print IO. Element of A dot parent. Alright, we're deleting this, we're making a new one. Okay, central simple algebra over rational field of degree 2. Oh, that's crazy. And now, if we define x to be, okay, so if we do, so xy equals gens a dot ring, and then do a is central simple algebra lm of a x. Oh, CSI. Element of central simple algebra over rational field of degree 2. Oh, that's so cool. That's so cool. So I'm just going to do one other. Okay, so this should be central simple algebra over field of 7 adic numbers of degree 2. Fuck yeah, that's so cool. Wow, big win. I mean, it took fucking forever to get here. I can't even imagine how long it took the people that made the macros for abstract algebra. I mean, holy shit. Whack. All right, great. We're done. Thanks for joining me. See you next time.